Our next speaker gets a little more introduction than I allowed myself or everyone else, because our next speaker is not a Toastmaster, although she did attend Toastmaster meetings for many years as a child. And of course, I personally attribute much of her success to the fact that she attended Toastmasters and learned the skills of those. But our next speaker is Dr. Tina Silva Jameson, our youngest. I had to twist her arm a bit to get her here, so I so appreciate that she did come. And her topic is, it really does take a rocket scientist. It really does take a rocket scientist, Dr. Tina Silva.
You're muted, Tina.
Okay, thank you, Mr. Toastmaster. I'm sure people have heard that saying, it doesn't take a rocket scientist to do this. And in my house, it's a funny joke. My husband thinks he's super funny because he says that to me all the time. Except in my instance, I really am a rocket scientist in every sense of the word. So I prepared a presentation for you all today to explain what it is that I do, because I'm not a normal rocket scientist. I do something very different than the standard rocket science. So most people know about the space shuttle or rockets when you hear about a SpaceX launch. This is the famous rockets that everybody knows about. And the whole purpose of a rocket is to get something into space, whether it be people or a spacecraft or an interplanetary mission that someday we're going to go to Mars. The spacecraft is up into space for over 15 years, generally. Have you ever thought about how does that spacecraft stay in the sky? That is the type of propulsion that I work on, which is very different than the rockets that everybody thinks of. NASA has a new program called Artemis, and it's been in the news lately, where its whole goal is to bring men and women to the moon in the next decade. And they want to have a presence at the moon. They want to build a space station around the moon, and it's called the Lunar Gateway. And I have a picture here on the right that shows a rendering of what it's going to look like. And it's this little space station that will orbit the moon, and it's a landing pad for the astronauts when they go from Earth to the moon. They can stop at the gateway on their way home and then come back. This entire gateway is possible by the type of propulsion that I personally work on, which is called electric propulsion. But first, I want to give you a little bit more about what is this gateway. It's a little station around the moon that has this power and propulsion element. That's the element that I work on. It has a halo, which is a habitation and logistics outpost. So this is where the astronauts will inhabit when they're there. There's going to be several different elements that will come along, more human habitation, a refueling module. There will be the Orion spacecraft that will come and dock. And this is truly an international space station around the moon. This power and propulsion element is not only very special to me, it's very special in the way that it's going to work and keep this space station around the moon. It has to have all of the propulsion and power to keep this station around the moon for over 15 years. And the International Space Station is refuelable. There are missions that come up all the time to refuel it. This spacecraft is designed to only be refueled once. And how does he do that? How can you keep something around the moon where humans are coming and leaving every year with refueling at one time? And that's with electric propulsion. That's what I do. So here's one of my most favorite images of an electric thruster, and it's got this amazing blue glow. But what is electric propulsion, and why would you use it? The rockets use chemical propulsion, and they're amazing. But electric propulsion has a very different function than that chemical propulsion. So this is an example that I like to use. And there's some science on here, and I left it just because I'm a scientist. I really am a rocket scientist. We use equations that governs everything that we do. If I think about a payload, which is this green dot here, and I want to get that into space, I need a lot of chemical propulsion to get this little tiny payload into space. And so here's a rocket. I have to have an enormous rocket to get this little tiny green payload into space. If I use electric propulsion. Electric propulsion is on the order of 10 times more fuel efficient than the chemical propulsion. So I can take this same payload, I have to supply power to it, but once I get that power and I have my electric propulsion, I can go to a smaller rocket, use 10 times less fuel, and get the same payload up into orbit once you're in space. So my analogy that makes sense to most people is that chemical propulsion, what you see on the SpaceX rockets, is like a Hummer. It's flashy, it's really big, it's extremely inefficient. And then there's electric propulsion, where it's not as flashy, but it gets the job done, it's very fuel efficient, and that's like a Prius. What some of you may not know is that you actually see rocket propulsion every day. For those of you that have Xenon headlights, that is the same technology that is used for this electric thruster. Inside your light bulb, if we can remember way back to high school chemistry, there's an anode, which is positive, a cathode, which is negative. The cathode emits electrons. There's an anode, which is going to attract those electrons, and then there's some neutral gas around it that gets ionized, and that's what makes that blue glow. It's the same thing. That's what happens inside your Xenon headlight in your car that we use to make, on the PPE element, we have the world's most efficient and most powerful thruster that is going to be flown in electric spacecraft. And we have 3 of them on the back of the PPE. And this is a picture of it firing in a vacuum chamber. And I like to call this the world's most expensive light bulb, because that's what we've made, is we have a light bulb here that's in our car, and we're putting something that's far more powerful, but it's the same technology, and it's actually going to keep the Lunar Gateway around the moon. This is also one of my favorite images, where it's a rendering. Obviously, it hasn't happened yet. We're supposed to launch probably in 2025, and you can see all this blue glow in the back. And this is how we're going to launch. In our rocket in 2025, we're going to have the power and propulsion element and the very first element on the gateway, which is Halo. It's so humans can come and be in the round element that you see in that image. So back to the Hummer and the Prius analogy. I like to joke that a rocket, it's 8 minutes into space. So after 8 minutes of all the smoke and fire and the flashiness, it's done. And then you drop off your spacecraft in orbit, and then now it has to get somewhere and stay somewhere for the next 15 years. So we do that with electric propulsion. And this is very special. NASA has only flown 2 of these electric satellites in its entire history. This will be the 3rd satellite that NASA flies. My company's name is Maxar. Maxar has over 35 electric satellites in orbit that uses this same technology. And so for me, I look forward to looking up in the night sky in 2026 because it's going to take us a year to get to the moon. Again, we're more fuel efficient. We're not very fast. We're not flashy, but we are way more fuel efficient. And I'm going to look up in the sky, and I'm going to know that humans are landing on the moon and coming back to this Lunar Gateway by what I do on an everyday basis by making the world's fanciest, most expensive light bulb on the planet, Mr. Toastmaster.